All right, I hear recording in progress. Okay, we're on to 8.1 on arc length. I'm actually almost done with this section. So we may have a somewhat short session today. I should be able to knock off 8.1. And rather than just stopping, I'll sneak in a little bit of 8.2. And more than likely, we'll still end a little bit early. Okay. All right, so we're doing arc length. I should be pretty much close to done 8.1 and sneak in some of 8.2. Okay, so we're doing arc length. Formula that you want on your cheat sheet. Page 545, box number 3. Arc length, integral from a to b, radical 1 plus dy dx squared dx. That's if y is a function of x. If you have x as a function of y, on page 546, box number 4. And you really only need this one, I think. Integral from c to d, radical 1 plus dx dy squared dy. Okay, y is going from one limit to another limit. Okay, so we did a bunch last time. I'll do a few more today. And you pretty much just plug it into the formula and then do the integration. All right, so I'll show you problem number 15. Yeah. By the way, you don't have to graph these problems. The 13 was crossed off because 13 is what it was in the previous edition. But it looks like it's 15 in our text now. Y equals ln secant of x. Don't graph it between 0 and pi over 4. Okay, so there's a curve, and you want to find the length of the curve from 0 to pi over 4. That's all. And ignore any dates that you see here. All right, so by formula, I need dy dx. So what's the derivative of ln secant of x? Well, 1 over secant of x times the derivative of secant x, which is secant x tangent x. After cancellation, you get tan x. Okay. All right, so the derivative of this thing is tangent x. I now want 1 plus dy dx squared. That's 1 plus tangent squared x, which very conveniently is secant squared x. So this thing goes underneath the square root. So what happens when you take the square root of secant squared x, right? So by formula, I want the integral from 0 to pi over 4 of radical 1 plus dy dx squared. Dy dx came out to be tangent. Square it, tangent squared, add 1. 1 plus tangent squared, which is secant squared. Square root of secant squared x is secant x. If I'm between 0 and pi over 4, first quadrant, you don't have to worry about plus or minus. So I'm integrating the secant. Okay, and you can put this on your cheat sheet if you want. Integral of secant, you might recall, is ln absolute value of secant x plus tangent x from 0 to pi over 4. Okay. Then a little bit of trig after that. So pi over 4, 45-degree angle. The point on a unit circle that it touches is radical 2 over 2, comma, radical 2 over 2. At an angle of 0 degrees or radians, you're over here, which is 0.10. So ln secant of pi over 4 is the reciprocal of the cosine. Cosine of 45 degrees is radical 2 over 2. Flip it. You have 2 over radical 2. 2 over radical 2 is radical 2. Plus tangent pi over 4. Tangent of 45 degrees, you might recall, is 1. Minus natural log of, okay, plug in 0. Secant of 0 is the reciprocal of the cosine of 0. Cosine of 0 is 1. Reciprocal is 1. Tangent of 0 is 0. So I have ln of 1, which is 0, so that crosses out. So my final answer is just ln radical 2 plus 1. And I dropped the absolute values because this is a positive quantity. Okay. All right, so that's that. And then 17, the cross off was because in the previous edition it was 15, but I believe it's now 17. Yes. Okay, so y equals blah, blah, blah from 1 to 2. Notice what we're doing. We're finding the arc length. Whatever this thing looks like, okay, from 1 to 2, if you were to walk along this, we're finding out the length of the arc. If I were to walk along this, what's the length? And this is not a straight line either. We can find distances if they're straight lines, but what if they're curves, right? Well, we have a way to do it now. So for this crazy looking curve, whatever it is, there's a quadratic and natural log combined. So whatever, between 1 and 2, we're able to find the arc length. Okay, so what's the derivative of this guy? So 1/2 x and minus 1/2 x to the negative 1. It's 1 over x. I'll write it as x to the negative 1. Square it. So dy dx squared 1/2 x minus 1/2 x to the negative 1 squared. This is like a minus b squared, which is a squared minus 2ab plus b squared. So if I square this, I have 1/4 x squared. Square this, 1/4 x to the negative 2. And again, Mr. Stewart seems to like this theme quite a bit. The middle term, the 2ab, just comes out to be minus 1/2. Minus 2, well, there's a minus, times that, times that. So 2 times 1/2 is 1. There's a negative 1/2. And then x times x to the negative 1 is 1. It's x to the 1 times x to the negative 1, which is x to the 0. X to the 0 is 1. Or you can think of this as x times x to the negative 1 can be thought of as 1 over x. So what's x times 1 over x? Well, that's also 1. So the minus 2ab term comes out to be negative 1/2 once again. And then this theme happens again. If you add 1, all that happens is the minus 1/2 changes to plus 1/2, right? So dy dx squared is this. There's a negative 1/2. Add 1, all of a sudden it's positive 1/2. Then if you look at this and this, you say, hey, it's the same thing. So if I refactorize it, I get the same thing, except instead of a minus, it's a plus, which essentially means if you look at this and say, oh, I don't know how to factor that. Yes, you can. Just look over here, put the exact same thing. See how I copied this exactly here, except instead of a minus, it's a plus. Okay? And you can confirm that if you actually multiply this out, you get this back. You can check it. A squared, right? 1/2 x squared is 1/4 x squared. B squared, 1/2 x to the negative 1 squared. 1/2 squared is 1/4. X to the negative 1 squared is x to the negative 2. And see if the middle term does not come out to be plus 1/2, 2ab, right? 2 times that times that. Again, 2 times 1/2 is 1. There's the 1/2. And then x times x to the negative 1 is x to the 0, but then there's a 1 there, which is 1. So it is indeed 1/2. So when I do my computation, I've got the integral from 1 to 2 of the square root of 1/2 x plus 1/2 x negative 1 squared. So again, that comes out very nice because if you have the square root of a square, just take off the squares. I don't have to worry about plus or minus. I'm between 1 and 2, everything is positive. So no need to worry about absolute value. So the next step I have to go up, but I'm just integrating 1/2 x plus 1/2 x and negative 1, which I decided to factor out the half just to make it easier on me. Okay, if I take out the square root stuff, I just have that and that, take out the half, right? So I have x plus x at negative 1, x plus x at negative 1. All right, so that's x squared over 2. And integral of 1 over x is ln absolute value of x from 1 to 2. Okay, so plug in 2. 2 squared is 4 divided by 2 is 2. Plus ln absolute 2 is 2. Minus plug in 1, you get 1/2 plus ln 1. ln 1 is 0. Okay, so I have 1/2 of 2 minus 1/2, which is 3/2, plus ln 2. And you can stop there if you wish. Just leave it alone. That's good enough. All right. So that is it. That's all I was going to do in 8.1. My original goal was to just get up to 8.1. So technically I could just stop now, which is too early. Okay. So just in case something goes wrong or I have to get sick or, internet goes down, I'll sneak in some of 8.2 and we'll probably still finish early. Okay. And I notice we still have some buffer day at the end before our next exam on the 15th. A reminder, there's a built-in buffer day on Wednesday, the 13th of October. There's a flex day, which means no classes for CSM. Teachers have to meet, but you guys don't have to meet. And that's just not my class, it's all classes, all CSM classes. All CSM classes are closed Wednesday the 13th for CSM flex day. Okay, so there's a built-in holiday there, so to speak. All right, so I'll introduce some of 8.2 just to get a little bit ahead, and we'll probably still finish early. Okay. So 8.2 is on area of a surface of revolution, page 551. Okay, so some things are the same as something we've seen before, and some things are different. And let me look at page 552. Okay, suppose I have this function here, spin it about the x-axis. You say, we've already done that. You're right. We've done it before. Only we're doing something a little bit different. Okay, so if I take this thing and spin it about the x-axis, there's what it looks like. It kind of looks like a vase, sideways vase, maybe. Okay, before we were considering the volume of that figure. The only difference now is we want to consider the surface area. So if I were to paint the outside, okay, no top, no bottom. If I were to paint the outside, right, what would the surface area be? So we're doing solids of revolution again, spin about the x-axis, y-axis, and so on, except now we're not considering the volume, we're considering the surface area, right? So if I were to paint the outside, what am I getting? Okay, so we're doing surface area of revolution, area of a surface of revolution. And again, I'll hasten to add, these two sections are the only sections we're doing in chapter 8. So we are not, there is more stuff in chapter 8, but we're not scheduled to do them. Okay, so other applications to physics and engineering, you might get that in your physics class or your engineering class. Okay, applications to economics and biology, some probability, right? So we're not required to cover those topics, but just to let you know that they're there, they actually exist. Okay, so how do I do stuff like that? So here's a typical slice. What we always do in calculus is we slice up the region. So the interval from A to B, suppose I gotta go chop, 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 right? Okay. Here's a typical slice. So I'll make the argument if I'll figure out the surface area of this band, and then make the same argument for all n of my slices. Chop it up into n pieces. Delta x gets very, very, very small, right? Take the limit as n approaches infinity and so on. Okay. All right, so we've played this kind of game before. How do I find a surface area? Well, if I make a cut and open it up, it almost looks like a rectangle for continuous functions. We're only considering continuous functions. Okay. And it's, can you see it's almost a rectangle? It isn't a true rectangle because the top and the bottom might be different heights, right? Like the way this is situated, if I slice and open it up, right, then it looks like this part would be a little bit smaller than this part, right? So it would not quite look like a rectangle. But if your slice is very, very small for continuous function, delta x is really, really tiny. Imagine delta x is, 0.0001 meters or whatever. Okay, the top and the bottom don't have much of a chance to change. So it's almost a rectangle, which is base times height. So if I cut and open, the base would be circumference of the circle, right? Think of this as a cut, open it up. That bottom would be the circumference. The height's a little bit tricky. It isn't a regular height, it's a slant height. There's a slanted height that it would have. Okay? It's probably more pronounced if you see it here, but it's not just delta x or delta y, it's the slanted height. Like so. So if I cut, like you get a ribbon, right? Cut, open it up. The height isn't delta x or delta y, it's this delta s, if you would, the slanted height. So it's along the arc length. Well, I already know how to find the arc length from section 1. We got a formula for that. Page 545, box 3. That's how I get the slanted height, arc length, which is the reason why 8.2 comes after 8.1 naturally. So you do 8.1 on arc length, and now 8.2 is based on the arc length. Okay. So for the almost rectangle, when I do this slice, right? Slice, open it up. I've got base times height. The base is the circumference of the circle. The height is this slanted piece here. I already know how to do that. It's this formula that we've seen before. Square root of 1 plus f prime of x of I star squared. And the base, essentially it's 2 pi r. All right, so if I spin it about the x-axis, the radius is this distance. You might recall from our previous work on disk and shell method, this height is y. So that gives us these formulas to put on your next cheat sheet, page 553. Okay, so if you, that's the rationalization, I guess, or the justification of why the formula works. You may not have understood anything I said over here with the derivation. That's okay. Just be able to use the formulas. Okay, S, surface area. Surface area. Integral from A to B, 2 pi y radical 1 plus dy dx squared dx. And this is rotate about the x-axis. So integral from A to B, 2 pi y radical 1 plus dy dx squared dx. Now, if it's dx, you have to change y into the function of y. Like if y is equal to, let's say, x cubed, then you got to put x cubed in here. And as you might expect, look at the difference between 5 and 6. I mean, do you want to put 6 on your cheat sheet? You may, but you can see the difference. Instead of y is a function of x, you have x as a function of y. So just like before, the only difference between this thing and this thing is instead of dy dx squared dx, you have dx dy squared dy. Very logical if you have x as a function of y. Right? So in a nutshell, you say to yourself, I don't understand what you were talking about over here. That's okay. What do I need to pass the test, right? Which is sort of what your main concern is. Okay, section 1, all you had was that, right? Section 2, put this in. If you're spinning about the x-axis, 2 pi y. So this is y as a function of x. If you have x as a function of y, then instead of dy dx, make it dx dy squared dy. They're actually saying another thing which I alluded to. This whole thing here, or this whole thing here, you can call it ds, which is a tiny change in arc length. Okay, so I'll draw you tiny pictures of what's this ds stuff. This is dx, dy, right? Tiny change in x, tiny change in y. So the tiny change in the hypotenuse is ds. Okay, and those of you going on to Calc 3, when you get to Calc 3, you'll be doing a lot more of ds stuff. Okay, so dx is a very tiny delta x, dy is a very tiny delta y, and actually when you get to Calc 3, give you a setup for Calc 3, you have a dz also, right? Change in x, change in y, and change in z, 3 dimensions, but you still have a ds. a rate of change along the arc length. So another way you could write this whole thing is this, although for now, you're not really going to need this. So I would suggest you probably don't need number 7, although it's correct, obviously, but ds can either be this thing here, radical 1 plus dy dx squared dx, or radical 1 plus dx dy squared dy. Okay, so dx, change, little tiny change in x. dy, tiny change in y. ds, tiny change in arc length, as it were. Okay. And for those of you going on to Calc 3, same thing. You have a dx, dy, dz in 3 dimensions, and you still might have a ds, although in this case it'd be in space when you're considering that. Okay, rotation about the y-axis. I think you can guess the change. If we spin about the y-axis, instead of 2 pi y, 2 pi x. And you may want to put this on your cheat sheet also. Again, that's very logical because if you spin about right, if you spin about the y-axis, the radius is now x. So the surface area is the integral of 2 pi x ds. Right? And again, ds is either that, if you have y as a function of x, or it's that, if you have x as a function of y. So that's what we're up against. All right, so quick summary of what do I want to put in my cheat sheet, right? We're taking a function. Whoops. Page 552. Y equals f of x. We're spinning it about either the x-axis or the y-axis once more. There's a picture. Can you say we already did that? Yes, we did that for volume, but now we're considering surface area. So not volume, not for this vase, how much water can I hold in the vase, but the surface area. If I were to paint the outside, no top and no bottom, how much paint do I need for the surface is what we're considering. Then rotate about the x-axis, use this thing, 2 pi y. If you look at this, you say that's the same as the formula from section 1, arc length. It is, because part of the formula, you need the arc length. Only difference is that you multiply by, well, it's 2 pi y if you spin about the x-axis, and it's 2 pi x. Let's see, where it go? Yeah, 2 pi x if you revolve about the y-axis. Again, what form of ds, the arc length, do I have? Well, if you have y as a function of x, to do this thing. If you have x as a function of y, then you do this thing. And yeah, it says formulas can be remembered. You don't have to remember it. You can put it on your cheat sheet, put it on your formula sheet. Make things easier on you. Okay. So again, here's some nice pictures that I can't draw because I'm not an artist, but spin about some axis, right? Looks like here we're spinning about the x-axis. Here is spinning about the y-axis where you get sort of a bowl. Okay, except we're not considering the volume, we're taking the surface area. Okay, if I were to paint the outside of this bowl, paint the outside of this, whatever, almost looks like a megaphone or a horn, okay, the surface area, that's what we have. Okay, so that's what we're up against. I was just going to do one problem maybe, and then stop. So we are now up to 8.2, which I originally wasn't going to start until tomorrow. So we're just getting a little bit ahead, and we'll probably still end early. So let's see, what are the problems? 8.2, 7 to 17 odd, and also number 12. Get that to you right here quickly. Page 555. Oh, it's all just down here, I think. Let me double check what I got here. 7 to 17 odd and 12. Yeah, it's all right there. So for those of you who don't have the book and aren't planning to get it, there it is. Try to focus it better there. All right, so maybe I'll just show you how one of them works. And that's about it. And then, yeah, after we finish 8.2, we're on to chapter 9. Excellent. All right. All right, so let me see if I can get through one problem. 8.2, number 7, first one. Y equals x cubed between 0 and 2. And by the way, I just mentioned quickly again, notice the form of the answer. 17 radical 17, 5 radical 5. This was probably 17 to the 3 halves minus 5 to the 3 halves. 17 to the 3 halves minus 5 to the 3 halves. That recurring theme, right? So for this section, in general, don't leave your answer to the 3 halves power. I want you to write 17 radical 17. I've talked about that already. Likewise, 5 to the 3 halves, 5 radical 5. Okay? And again, that will happen a lot. And it's really no mystery why, because the formulas involve integrating a square root, right? So unless something unusual happens, you're integrating blah, blah, blah to the 1/2. So if you integrate blah, blah, blah to the 1/2, you're going to get something to 3 halves naturally, and then some other stuff. I mean, it's not always that, you know, it's not 100% that they're all going to be that way, but it happens a lot. Well, you write your answer like that. Well, here it is, like this: 17 radical 17, 5 radical 5. That's 17 to the 3 halves, 5 to the 3 halves. Okay. All right, so maybe I'll just show you number 7, and that's about it. Find the exact area of the surface obtained by rotating the curve about the x-axis. Okay. Oh, I'm sorry. We were supposed to do some more problems on the next page. Right. And some y-axis. So 556, 15, and 17, I think, was also on our list. Yeah. Yeah, naturally, I had to give you something that's rotating about the y-axis. Of course, so there we are. Okay. All right, so 8.2, number 7, y equals x cubed from 0 to 2, spin about the x-axis. Okay, you don't have to draw out the picture, but I will just this one time, you should know x cubed looks like that, right? Go like that, spin it around the x-axis. So it kind of almost looks like a sideways volcano, right? Or if I turn the picture like that, spin it around, kind of looks like a volcano where the lava will come out here. Okay. Except this time I'm not finding the volume. I want the surface area of the volcano. Okay. All right, so by formula to find the surface area, just like section 1, I need dy dx. That's easy. 3x squared. I want 1 plus derivative squared, just like the last section. That's easy. 1 plus this thing squared is 9x to the 4th, right? Right, so surface area is 2 pi radius. In this case, the radius is y. And what's y? X cubed. So 2 pi y, 2 pi r, times the formula for arc length. So the problems are just like section 1, except this part was from the last section, right? And now you put in 2 pi r, which is either going to be 2 pi x if you spin about the y-axis, or 2 pi y if you spin about the x-axis. Here we're spinning about the x-axis, so 2 pi y, here it is. And then 1 plus dy dx squared dx. Okay, normally the 2 pi comes right out. The derivative of something with x to the 4th is going to be something with x cubed. So it looks like a u substitution. U equals 1 plus 9x to the 4th. Du is 36x cubed dx. There's the x cubed. I don't have a 36, easy. So in red, put in 36 inside and 1 over 36 outside, which means outside I now have a 2 pi and a 1 over 36. That combination gives me pi over 18. Okay, 2 pi over 36. And it's a definite integral, so I change the limits. So x is going from 0 to 2. What happens to u, right? Plug in. X equals 0, put a 0 there, u equals 1. Plug in 2, well, 145. 2 to the 4th power is 16. 9 times 16 is 144, plus 1 is 145. And I want you to notice an important principle here. By making this substitution, you could have a much different length of the integral. Okay, look at the original, x only went from 0 to 2. But look at u, it's going from 1 all the way to 145. That's possible. Okay. Because of this transformation, u is 1 plus 9x to the 4th, right? When x goes from 0 to 2, all of a sudden u goes from 1 way out to 145. So it's a much longer interval. That interval length is 144, whereas the original length was just 2. So that might happen. That's allowed. Okay, then I'm pretty much home free. So I have radical 1 plus 9x to the 4th is radical u. 36 x cubed dx. That's my du. And I got pi over 18 outside. And I'm now going from 1 to 145. Okay. So remember, that's the same as u to the 1/2. So when I integrate u to the 3/2, divided by 3/2 means times 2/3. Okay. So there's that 3/2 that we talked about before. Common theme. Okay, let's see what happened here. 2 cancels with the 18, giving me 9. 9 times 3 is 27. So pi over 27. 145 to the 3/2 minus 1 to the 3/2. Okay, 1 to the 3/2 is 1, right? 1 to anything is 1. If you go literally by the letter of the law, you take the square root of 1, which is 1, then you cube it, it's still 1. Again, please notice how to write 145 to 3/2. 145 radical 145. And I want you to write that. If you don't write it, I might take off points. This is considered simplified. Yes, they mean the same thing, but make it simpler. Right? How do I make this simpler? Write it like this. Again, the simplified is if you ask a typical person off the street who maybe had math, who didn't have math or hasn't had a whole lot of math, they would much more likely understand this than this. Right? Say, oh yeah, I remember something about square roots and you multiply by 145. But that, right, many more people are less inclined to understand what that was all about compared to this. So here's my final answer, pi over 27, 145 radical 145 minus 1. Okay. All right, so I was done for today, folks. I was able to finish 8.1, sneak in some of 8.2. So I'm a little bit ahead even for tomorrow and can still probably end early. All right, so anybody want to ask me a question? Otherwise, we're done for the day, folks. Let me stop to share quickly and check the chat if there's anything. Okay, any questions, please? All right, I don't see anything, so we're done for the day. All right, have a good day, everybody. See you next time. Okay,
Take care. Thank you.
Thank you.
Thank you.